In this video, we are presenting shape-shifting splats, real-time context translation for Gaussian splatting in VR. 3D Gaussian splatting was introduced by Kerbel and colleagues in 2023 and has since been the state of the art for photorealistic reconstructions and novel view synthesis. However, as you can see in this workflow description from the original paper, 3D Gaussians are static. Once trained, changes in the Gaussian splatting model are only feasible via complete retraining. Now, what if we want to encode different modalities of scenes into a 3D Gaussian splatting model? For instance, RGB and thermal data. Or what if an 3DGS asset should appear in a different style? With the original 3D Gaussian splatting approach, this example of a stylized Lego model from the synthetic NeRF dataset would require 3 separately trained Gaussian models. One model containing the original asset and separate model for each stylized asset. Rendering different modalities or styles would be therefore not possible with a single process. N appearance changes would require N separate 3D Gaussian models that have to be independently loaded, aligned, rendered, blended, and so on. This would also come with N times the rendering effort and N times the memory requirements. To mitigate this problem, we introduce shape-shifting splats. Our approach extends ScaffoldJS and allows all Gaussian attributes such as color, opacity, scale, rotation, and so on to be predicted by separate MLPs. As input to these fully connected shallow MLPs, we use voxel or anchor features and append a so-called control encoding to them. In the training, they condition the MLPs such that changing them triggers a shapeshift and changes the appearance and geometry of the predicted Gaussians. In the video, you can see the interpolation between the previously shown Lego scene and 2 stylized versions, all within one model. In the standard 3DGS pipeline, anisotropic 3D Gaussians are rendered. Their attributes change in the training phase via backpropagation through the differential rasterizer. Our method keeps this part of the rendering process unchanged, as we also rasterize 3D Gaussians. However, the attributes of the Gaussians, like shape and color, are first predicted via the scene-specific MLPs. As input to the MLPs, we apply input features. Now, these input features mainly consist of 3 parts. First, we use an anchor feature vector for a certain voxel-sized region. This vector is a trainable parameter and responsible for k number of 3D Gaussians. In our implementation, we set k to 10. Secondly, we append the viewing direction delta to this anchor feature. Note that this is only necessary for the color MLP. And finally, we concatenate our control encoding psi. In the training, this encoding corresponds to the specific loss and conditions the MLPs accordingly. At render time, it encodes the modality or style, which the MLPs should predict. Therefore, changing the control encoding triggers the shape-shifting mechanism. As control encoding, we choose to use a 1D Gaussian, depicted here in orange. This 1D Gaussian is simply sampled at certain locations and forms our control encoding. In this example, we encode 3 different styles in the training phase. With a mean around 0, the control encoding corresponds to no style, as you can see in this image here. A change in the mean of the Gaussian of the 1D Gaussian results in renderings of different styles. All of these styles are encoded within a single model. We can also add masks such that only certain parts of the image are stylized. In this example, we use a clip-based loss together with a text prompt to encode different colors of leather for the chair from the synthetic NeRF dataset, also into a single model. The masks are applied to the white armrest such that only the original green fabric is stylized. This showcases the usability of our approach in e-commerce settings. Another example is industrial inspection. Previously, 2 models would be required. Now we can deploy our method on RGB and thermal data to encode both modalities within a single model. The control encoding on the 2 ends of the spectrum, namely 0 and 1, corresponds to RGB and thermal respectively. Changing it triggers a shapeshift from RGB to thermal. As you maybe already saw in the video from the previous slide, we implement our method in Unity, where we adapt existing 3D.js render pipelines for our method. We use the AI inference library, previously known as Sentis, to run the MLPs, as they automatically employ custom compute shaders. Furthermore, we can bin the necessary data into GPU memory to avoid unnecessary CPU-GPU readbacks. As you can see in the video, we are able to import our shape-shifting assets into Unity. This is interesting, for instance, in gaming scenarios. A big challenge is the deployment on mobile VR devices. Usually scenes contain multiple hundreds of thousands of Gaussians, which need to be sorted, blended, and so on. So we try to reduce this computational burden by asking which Gaussians contribute little but take up a lot of resources. Therefore, we propose 2 rather straightforward engineering trade-offs. The first one is the distance threshold tau dist. This model of a nature scene from the mid-nerve dataset showcases that many Gaussians are far out. The rendering, which is here in red, contains only a small subset of the Gaussians visible from bird's eye view, visible here in the middle image and here on the right hand side. Therefore, when deploying a scene on a mobile VR device, we simply abstain from rendering Gaussians above a certain distance threshold. The second threshold is tau lambda, and this threshold is concerned with large Gaussians with a mean outside of the view frustum. In this scene from the thermal Gaussian dataset, we cull Gaussians with an eigenvalue above a certain threshold and the mean outside of the view frustum. An extreme example can be seen in this image here, where we showcase how a very, very low threshold affects the renderings. We apply runtime analysis on PC, PCVR and mobile VR with the MetaQuest 3. And as you can see here, all 3 device settings can handle object-centric scenes easily, such as the leg scene, with roughly 450,000 Gaussians. Larger scenes, with roughly 800,000 Gaussians, are only feasible on the mobile device with tau lambda and tau dist applied, as the render time without them would be above 160 milliseconds per frame. We also estimate the time that the shapeshift needs. Remember, when we change the control encoding in render time, the MLPs are queried and a shapeshift takes place. Here we evaluate the runtime again on all devices, PC, PCVR and standalone VR, and we measure the time when all MLPs are queried and when a single MLP is queried. While on the PC the runtime is negligible, inference on the mobile VR and PC VR scales with the number of splats. With 1 million splats, a complete shapeshift takes over 1 second on the standalone MetaQuest, while being below 10 milliseconds on the PC implementation. Still, our method is able to produce smooth renderings with shapeshifting between thermal and RGB on the mobile standalone Quest 3 as shown in this video. Besides runtime evaluation, we showcase that our approach is also able to reconstruct multi-layer anatomical data well, while needing less on-disk memory than other approaches. With this dataset, our method encodes different layers of anatomy. A shapeshift therefore performs the change in layers of anatomy. Furthermore, we showcase good reconstruction results compared to other RGB thermal datasets, Again, our method needs less on-disk data than other approaches, while achieving on-bar or better reconstruction metrics. Interestingly, we found that the reconstruction can benefit from training with both domains. Hence, when trained separately, we achieve worse metrics than when we train the model on both modalities together. Thank you for your attention.